Hey guys, here we are in chapter 6, looking at section 6.5. We're talking about rhombi and squares. With our new vocabulary, I think we need to just get a different point of view of what we are talking about, because I know you guys know what a rhombus is, and I know you know what a square is, but I want you to kind of see it in the whole scheme of things. So we've been talking about four-sided figures, which are called quadrilaterals, and our quadrilaterals can be broken down into two major categories at this time. And the one that we're going to talk about would be the parallelogram. We've been talking about that. Parallelogram. And the symbol for parallelogram is just a little tiny parallelogram where the opposite sides are parallel. You don't usually have to write these opposite sides in there. I'm just doing that for the sake of what we're doing here. And then there's this thing we haven't talked about, but we will, called a trapezoid. And a trapezoid is a four-sided figure, a quadrilateral, where exactly one pair of sides, no more than one pair of sides, would be parallel, right? So these sides cannot be parallel as a point of fact. And so we can talk about the parallelogram in some more detailed terms, because we know that if you have a parallelogram with one right angle, it's a rectangle because all four angles will be right angles. And let me see, let's draw it like that. There we go. Put a little angle there. So that is an offspring of the parallelogram. And then another offspring of the parallelogram is the rhombus. And a rhombus is a parallelogram where each of the sides are congruent. So let me draw that a little bit better. Sometimes I like to draw them like a straight up and down diamond. There we go. So boom, bap, bip, and bim. If you have this situation, you've got yourself a rhombus. And then weirdly enough, the rhombus and the rectangle create a very special, very special. In fact, it's a regular quadrilateral, right? Remember, regular polygons have equal sides and equal angles. So it creates the regular quadrilateral, the square. Okay, so sometimes I like to refer to this as the family tree of quadrilaterals. Okay, so we got a parallelogram, which just means the opposite sides are parallel. Trapezoid, its own branch, where you have exactly one pair of sides that are parallel, not both. And then here from the parallelogram, we can specify that a special type of parallelogram is a rectangle where each of the angles would be 90 degrees. And then another special type of parallelogram is a rhombus where each of the sides are equivalent. And then also a special type of rectangle or a special type of rhombus or a special type of parallelogram, because they all fall underneath, is the square, where each angle is equivalent and each of the sides are equivalent. So you've got your definition in kind of a weird way. All right, so let's take a look at this. So we've got these terms that you know how they go. They're like, if I've got this, then hey, here's the logical conclusion. So if we have a parallelogram that is a rhombus, meaning if we've got a parallelogram where all four sides are equal, then its diagonals are perpendicular. All right, so then we know that this is giving us that fact. Given a rhombus, the diagonals are perpendicular, and perpendicular, we know, means that they intersect to form a right angle, a 90-degree angle. This next one says if a parallelogram is a rhombus, again, we're starting off with the principle that we've got a rhombus, then the diagonals do something else that's interesting. The diagonals bisect each of the opposite angles, bisects each pair of opposite angles. So PR, that diagonal is going to bisect this angle P and bisect this angle R into two equal parts, meaning making 1 and 2 equal and 3 and 4 equal. And then it's going to do the same thing over here with N and P. But then, we can get kind of even more detailed in the fact that these sides, these angles must be equivalent to each other. So 7, 8, 6, and 5 must be equivalent, and 1, 2, 3, and 4 must be equivalent to each other. And I'm going to let you guys think about why that is the case. All right? Okay, cool. I know you're thinking, you're like, why is that the case? All right, let's take a look at the first example. Example 1, use properties of a rhombus. So they tell us that the diagonals of this rhombus, so they're confirming that this is a rhombus here, FGHJ, intersect at K. Use the given information to find the value of each measure. So here we've got F, J, H, and we're given that angle value is 82. Let me zoom in on this a little bit. So we're given that this angle value is 82 degrees. Let me put an 82 here. And then we're supposed to find K, H, and J. So our goal is to find this guy. Let's highlight that in red. And I'll make this a little bit smaller as I try to put that 82 in there a little bit neater. All right, so we've got that this is 82 degrees, and we need to figure out some other information. So what do you know? Well, you and I both, we just read the theorem that said this angle here has to be a right angle given the fact that it's the intersection of the diagonals of a rhombus. So we start off there. We know that's 90. And so if that's 90, and then, okay, that's kind of helpful, but sort of not really. That's 90. I can find this angle over here, right? So if this is 90 and this is 82, this is 90 and this is 82, this angle over here has to be pretty small, interestingly enough. This angle here has to be pretty small. Why am I finding this angle? Because I know that from a previous theorem that the opposite angles, let me just do it in big old bold, these two opposite angles have to be congruent, right? The opposite angles of a parallelogram are congruent, and a rhombus is a parallelogram, therefore the opposite angles in a rhombus must be congruent. And then what I also know is that the diagonals of a rhombus bisect all the angles, so then all four of these are equal, right? So if I can find the measure to angle F, angle JFH, which I'm going to mark here in, I guess, green. If I can find this angle measure, then I'm already finding this angle measure, and so I should be in good shape. Does that make sense? I hope it does. I hope so. So we know that 82 plus this mystery angle, angle JFK, and plus the measure of 90 degrees, all that has to equal 180. I can subtract 90 from both sides, and then I get that 82 plus the measure of angle JFK has to equal 90, right? And then if I subtract 82 from both sides, I get that the measure of angle JFK is 8. It's 8 degrees. Does that make sense? So it doesn't look like it in this picture, but given the detailed information that we got, that absolutely has to be the case. Let's go ahead and see if we can use this image to answer this one. So we're given that GH, that's this segment here, GH is this length, and JH is this length. We're supposed to find X. Well, here's what we know. All the sides of a rhombus are congruent, so we know that these guys must be congruent to each other, meaning GH must equal JH. And because of that, I can set the length of GH, which is x plus 9, equal to the length of JH, which is 5x minus 2. And so, of course, I'm going to do what I always do. I'm going to solve it by moving all my x terms over to one side. You guys know I say this like every time, every time. Move the 2 over here, and I get not 12, which I wanted, but I'm going to get, I'm going to get 11 is equal to 4x. Making sure I did everything okay. Subtract x's on both sides, move that over there. I'm feeling good about myself. I'm going to divide both sides by 4, and I get a fraction. I know the textbook has lulled me into thinking that if it doesn't come out even, it's not right, but I think we're doing all right. So 4 goes into 11 how many times? Like 3 times with a remainder of 3. So 3 3/4 is our answer. So that's the value of x, and that's what we were asked to find. Here's a little graphic from your textbook that I thought was interesting. It's not exactly the family tree of quadrilaterals that I have, but it is a look at parallelograms and saying, okay, here are the characteristics of rectangles, here are the characteristics of rhombi, and in the center, in the overlap of this Venn diagram, we have squares because rectangles and rhombi, if you have a quadrilateral that is both a rectangle and a rhombi, it's also got to be a square. So now these theorems are going in a different direction. They are giving us conditions for a rhombi and a square. So conditions to see whether we have a rhombus or a square. And so let's start with 617. If the diagonals of a parallelogram are perpendicular, so what they're saying is you got to you've got a parallelogram, you look at it and you find out that the diagonals are perpendicular, guess what you got? A rhombus. All right. So it's a condition for saying I'm identifying you as a rhombus. Let's look at this next one. If one diagonal of a parallelogram, only one, right, mind you, if one diagonal, you got this parallelogram and one diagonal happens to bisect the opposite angles, then that parallelogram is a rhombus. All right. And they're telling us what is the converse of. And remember, converse is when you switch the hypothesis and conclusion. So we're kind of switching them around and saying, oh, well, if you have this, then you've got this. All right, let's take a look at this next one. In 619, if one pair of consecutive sides of a parallelogram are congruent, then that parallelogram is a rhombus. So if I knew that ABCD is the parallelogram, and I can say that AB and BC are congruent, then all of it's congruent. And that is a short proof to show that, because you know that the opposite sides are congruent when you have a parallelogram, and therefore you'd have all four sides being equal if you did that. So let's look at this last one. If a quadrilateral is both a rectangle and a rhombus, then it's a square. And we saw that since the beginning of our lesson today. If a quadrilateral is both a rectangle and a rhombus, then it's got to be a square. So example 2 gives us the opportunity to demonstrate some of what we just talked about. Proofs using properties of the rhombi and the square. So here it is. We're given that this whole thing is a parallelogram, and then we're told that this triangle here that I'll have highlighted in yellow, JKL, this triangle, is isosceles. We're asked to prove that JKLM is a rhombus, and this will be a rather short proof of which I'm going to give the highlights. The one thing you want to do is state your given information, and from this given information, we can say that JK is congruent to KL. And you can say that JK and KL are congruent. These are the sides I'm talking about because of the definition of isosceles triangles. The definition of isosceles triangles, right? So if JKL is isosceles, two sides have to be equivalent. JK is congruent to KL, definition of isosceles triangles. All right, great. The next thing we need to do is employ one of the theorems that we talked about just now, and this one looks like the one. If a pair of consecutive sides of a parallelogram are congruent, then the parallelogram is a rhombus. So from there, we can pretty much go to saying that JKLM, that a parallelogram JKLM is a rhombus based on the theorem above, that if a pair of consecutive sides of a parallelogram are congruent, then the parallelogram is a rhombus. And so there were really only two major points to this, pointing out that given the fact that this is an isosceles triangle, two sides are equivalent, the two sides are consecutive, and there are also two consecutive sides of a rhombus. Therefore, JKLM is a rhombus by theorem 619. All right, this isn't a hard example, but we're going to pick it up in the next video. So I'll give you guys time to prepare some space so we can do a little chatting. I just want a little bit of time to talk about it, and I'm not going to have it in this video. So let's go ahead and pick up at video 6.5, and I look forward to talking to you guys very soon.